last video of the section. Imagine having a section with only 4 videos that aren't 30 minutes long. Hopefully this one will maybe be a little long because we have a lot to do. So we're going to go back to our RC circuit that we've been dealing with for a few sections in this class, where there's going to be some voltage source, and that voltage source is going to change over time. And then it's going to go across some resistor with some resistance R. That'll be a parameter that we'll have. And there's a capacitor C. There will be some parameter for the capacitance that we'll give. And what we're curious specifically about is the voltage across the capacitor over time. So it's certainly going to be related to that voltage source, which is going to change over time, but it is also kind of exponentially decaying outside of that input. So nice box, by the way, nice rectangle. Okay, so here our voltage source is going to be 2 times u sub 4 of t e to the negative t minus 4. And before we even introduce a differential equation, I want to talk about what this voltage source even means or looks like. Because we know what it means, and we're just going to take a couple steps to get there. Okay, so first off, if we're just like doing a little sketch, we know what 2e to the negative t looks like, right? 2e to the negative t starts at 2, exponentially decays. And then we know what happens when you write it like this. We know that's a horizontal shift to the right, 4 units. So we're expecting a horizontal shift to the right. Again, this is still 2, but now this is 4. It's just the same graph, shifted right 4. And all this is again, normally that would continue everywhere. This is just a Heaviside function which says, all right, we're 0 all the way over here, and then we jump up. So I think this is our voltage function, capital V of t, right? We've introduced the stretching factor, introduced the Heaviside portion, and then, yeah, the horizontal shift as well. So this is our voltage source over time. So if this is our voltage source, what's going to happen is, well, there's no voltage for the first 4 seconds. We expect our system to exponentially decay. There's no voltage, we're going to run out. But then after 4 seconds, we are going to have a voltage source that's, much higher. It's going to jump up. We're going to flick a switch. And then our input is exponentially decaying. So we're going to start at 4 by flicking a switch. Maybe that is like a big burst, but that burst itself, that the voltage source itself is exponentially decaying. And we're going to see what that's sort of going to look like. So to do that, let's actually introduce an initial value problem. Again, these are unrealistic numbers. I'm choosing unrealistic numbers to make things a little nicer. For us, C will be 1/3, R will be 1, and that's going to give us 1/3 dVc dt plus Vc equals 2 u, this is our voltage right-hand side, u of t, e to the negative t minus 4, where our initial voltage across the capacitor is 5. All right, so this is going to be our initial value problem that we want to solve. Again, somewhat unrealistic parameters just to make our lives a little easier. We know what our voltage source is going to look like, and we're going to start with some qualitative analysis. Remember, this is a linear non-homogeneous differential equation. It's not autonomous. There will be a homogeneous solution. There will be a particular solution. There's a couple different ways that we can solve this. One of them would be to use the linearity principle, but we can't really do that because our right-hand side is not continuous. So we're going to use the Laplace transform to solve this. But before we do that, right, we could, if we wanted to, we could write this as a piecewise function, but I actually don't think I necessarily want to do that. We could do it like the similar way that we did it in video 2 of this section. But really quick, we'll just do some very brief, somewhat informal qualitative analysis of what this is going to look like. Well, we're starting off at 5. We're starting off at 5, and there's no voltage at the start, right? There's no voltage for the first 4 seconds. So we're starting off at 5, there's no voltage. What do we think is going to happen? We're going to exponentially decrease. And then as soon as this happens, as soon as we're 4 seconds in, or whatever t represents, we now have a voltage source. So now there's a voltage source. So we're kind of going to exponentially grow to this curve. So be very careful. Just because the voltage is discontinuous doesn't mean that the voltage source is discontinuous, but it doesn't necessarily mean that the voltage across the capacitor is discontinuous, right? If you think about what we had way back here, where there was a big discontinuity in the right-hand side of our differential equation, but it was still we still had a continuous solution because the change is going to jump. The slope is going to change. The slope will be discontinuous, but this is not actually going to jump anywhere. So we'll expect it to like immediately start like approaching that v sub t. Like, right, specifically, we know v sub t looks like this. So we're going to like exponentially grow to it and then kind of like follow it a little bit. Or maybe we like overshoot it a little bit and we're going to decay. Who knows? We're going to get some kind of hump. It's going to get steep. And then we'll have more exponential decay because, again, we're eventually losing our voltage source. It's decaying over time. So this one's a little bit less clear. We could do some more advanced qualitative analysis to figure out what we expect. But the idea is that we know there's going to be some kind of bump, and I don't know what it's going to look like. There'll be probably a slope discontinuity, so like the slope changes immediately, some kind of bump, and then again, we do have exponential decay again. This is what we might expect from our solution. And we could get a better solution if we actually paid attention to what happens when this is an exponentially decaying voltage source. But that's an idea. So let's do it. Let's Laplace transform to solve this equation. This is a fantastic opportunity for you to pause the video and see how much of this you can do on your own. Okay. So if we take the Laplace transform of both sides, we remember that the Laplace transform is a linear operator. So when we Laplace the left-hand side, we can actually make our lives a little easier and immediately use the linearity property of the Laplace transform to factor out the 1/3 and then split this up across addition and get that. And then similarly on the right-hand side, oh boy, okay. The right-hand side looks a little scary, but don't worry. We can still factor out that too. And we just talked about a tool to deal with this. Of u4 of t, e to the negative t minus 4, okay? So let's work with the left-hand side first, and then we're going to unpack the right-hand side. So the left-hand side, we know this is going to be 1/3 times, what was that property? What was the Laplace transform of the derivative? If hypothetically I didn't remember, I could check our sheet, which has some notes. And also, those exact notes are going to let us deal with the right-hand side. This was that shifting property that we did in the last video, and this is from our first section, 6.1. Okay, so that's going to be S times the Laplace transform of just VC minus our initial condition, which is 5. And then we still have the Laplace transform of VC over here. And now we have to use that new property that we had. So let's be very careful with our notation here. Right? This is what we're looking at. We have the Laplace transform of a Heaviside function, and specifically a is 4 here. So we're going to look at this and say, okay, a is 4. And then what is f? F of t minus a. Be very careful. All right, we want f of t minus a here. So f of t minus a is going to be e to the negative t minus 4. So f of t is just e to the negative t as a result. Okay? So f of t equals e to the negative t. So now I think we have the information we need to apply this property. It says that's going to be e to the negative as. We know what as is. E to the negative a, which is 4 times s. And then I'm actually wondering whether we're making our lives harder and we can just leave this as the Laplace transform. No, I don't think we can leave it. Anyway, we'll find out later. E to the negative 4s times f of s. What was f of s? F, capital F, remember, was the Laplace transform of f. So it's going to be multiplied by the Laplace transform of f, which we know. The Laplace transform of e to the negative t, that's just a equals negative 1. It's going to be 1 over s plus 1. And again, s has to be greater than negative 1 to use this property. Okay, now we solve for VC. We applied our Laplace transform to everything that we can apply for the Laplace transform. We'll get the VCs by itself, we'll do some algebra, and then we'll undo it with the inverse Laplace transform and hopefully get an answer that looks something like this. So if we do that, I kind of want to multiply everything by 3, so I think I will do so. If we multiply everything by 3, we can distribute that 3. And then we're going to get this. So we get the Laplace transform applied to VC. That's being multiplied by the coefficient s plus 3. And then we have a minus 5. Oh gosh. I'm doing too many things in my head. This is dangerous. We're going to add the 5 to the other side. And then that's 5 plus 6 times all this nonsense. This is going to be 6 times e to the negative 4s all over s plus 1. Okay? So let me just double check, right? We multiplied everything by 3, which made this by itself. That's why there's a minus 5 that we added over. There was a coefficient of s on the Laplace transform. And then there was a plus 3 over here on this Laplace transform. The right-hand side just became 6 e to the negative 4s, and it turns into division. So I think we're pretty good. Now we're almost done. Sort of, not really. We're almost done with one part, right? We can solve for the Laplace transform. Divide both sides by s plus 3. We get 5 over s plus 3 plus 6 e to the negative 4s over s plus 1, s plus 3. Love that right-hand side. And we can now use the inverse Laplace transform. Woo! Because the inverse Laplace transform of the first one's not bad. Right? That's just going to be an e to the negative 3t. This one, we get to use our shifting idea, and we get to use partial fractions, both. How exciting. So, let's do that. Vc of t, the velocity across the capacitor, is going to be the inverse Laplace transform of this, which again is just, let's check our notes, but I'm pretty sure it's 5 e to the negative 3t. Right? It's just, the 5 comes out in front. A is just negative 3. Yep. 5 e to the negative 3t plus the inverse Laplace transform of this nonsense. Okay? So I'm going to leave the 6 up here for now. Inverse Laplace transform of 6 e to the negative 4s all over s plus 1, s plus 3. And then what we have here, we're going to need to go off to the side and do some partial fractions. So let's do that. What is 6 divided by s plus 1? S plus 3. Well, that'll be some number divided by s plus 1 plus some other number divided by s plus 3. Multiply out both sides by the least common denominator, a times s plus 3. And I thought about not doing this live on the video. I was like, they can do partial fractions by now. And then I thought, my students probably still hate partial fractions. What if we just do it quickly so they can skip through it if they want? And again, remember, you can always fast forward, rewind, slow down, speed up a math video. But if they wanted to see the steps, I'll let them see the steps. But I know I'm going very fast. Reminder to pause the video always. Any math class you're taking, pause the video, catch up, think about things. So if s is equal to -3, what do we get? We get 6 is equal to -2b. b is -3. And if s is -1, we're going to get 6 equals 2a. So a is equal to +3. You're hopefully really noticing a pattern when we do these partial fractions to these simple things. So what do we have here? And I kind of want to stay off to the side, but maybe I shouldn't. We have that this is equal to 5e to the -3t, plus this becomes, right, a is 3. So this becomes 3 times the inverse Laplace transform of e to the -4s over s plus 1 minus 3 inverse Laplace transform of e to the -4s over s plus 3. And maybe we should have even written it a little bit different as well, so that we could use this property that we just introduced in the previous video. So we see that a here is going to be, what is a going to be? It's e to the -as. A is going to be 4 in both of these. So that's going to be a Heaviside function that's going to pop up. We should not be surprised that a is 4 here, because our Heaviside function, right, our electrical switch is getting turned on at 4 seconds. So this should not be surprising. A is equal to 4. And then we just look at each individual function. All right, it's the function e to the -t and e to the -3t getting shifted by that much. And again, to really see that modeled, look back to what we did over here in this process. Okay, so we're going to get our functions e to the -3t plus 3 times the Heaviside function, u sub 4 of t, times, again, this is e to the -t, but being shifted right 4 units, like so, minus 3 Heaviside function, e to the -3t, and again, t is getting shifted right 4 units. Okay, and this should be what we have. Let me just double check that I did not make a silly mistake. This is indeed what we have. And again, really the long process is what we did in the previous video, where we split this up, identify what capital S and little f are, use the transform, use the horizontal shift, and then really go through it like that. Okay? So we could clean this up a little bit and get our final answer. And we can graph it. And let's see if our graph on Desmos looks like our qualitative analysis. 5e to the -3t. Let's factor out a 3 times our Heaviside function. Notice you might want to factor out an e to the -t minus 4, but because of properties of exponents, you actually can't do that. Try to factor it out and then double check your answer and see what happens. So don't factor that part out. We're left with e to the -t over 4. Sorry, -t minus 4. And then minus e to the -3 t minus 4. And I don't think there's anything you can do to simplify this. Because remember, we really have that property that e to the, like, s times t, like when things are multiplied, which is factoring is multiplication division, the only property we really have is like this. And that's not going to help us here. So, like, I'm pretty sure we're just stuck here. Let's check our answer. This is saying the voltage across, before we even graph this, we can do a little qualitative analysis just from our analytic solution. What's happening is for the first 4 seconds, this doesn't exist, right? For the first 4 sections, we just have exponential decay starting at 5. That's what we expected, right? For the first 4 sections, we expected to have exponential decay starting at 5. And then I said there's some kind of bump, whatever that means, and then we exponentially decayed. I have an extra thing here, and I always keep jumping to it instead of the other things. So is that what's happening? Are we getting a little bump and then still decaying? Well, remember this at 4 seconds just becomes a 1. So yeah, after 4 seconds, we do get a bump, right? We get bumped up. It actually does look a little discontinuous. It'll be interesting to see if it is. And then, yeah, we're still getting exponential decay. At t equal, oh, it actually is still continuous, because even though this is jumping to 1, what happens at t equals 4? At t equals 4, these exponents are 0. We get 1 minus 1 is 0. So at t equals 4, this piece is still 0. So our answer is still a continuous function, which is pretty cool. It's not differentiable at 4, but let's graph it. So I already input this into Desmos. So I defined the Heaviside function at 4. I could have just defined a generic Heaviside function by making a parameter, but I didn't. And then I graphed our equation, which again should hopefully look like what we just found. I graphed our solution. Yeah, this is all right. This is looking like what we found in a slightly different order, but looking like what we found. So if we graph it, whoa, look at that. Look at that. What our guess? Look at that. I mean, it shouldn't be that surprising, right? Like, obviously I saw this picture, but the logic, right? And so a couple things are different from our qualitative analysis, right? It started exponentially decaying very fast. E to the negative 5t is very fast exponential decay. But then, yeah, we got a little bump. And again, just like before, what I want to do is show you what we're adding. And let's get rid of the Heaviside function. So you can see, right, that if we didn't have the Heaviside function, what we're adding to this thing that is almost 0 at this point, right? There's no voltage, no real amount of voltage at 3 seconds in. And then this is essentially kind of the solution to the differential equation if there were, you know, if we weren't starting that at 4. Which is kind of cool. That's neat. And it's pretty cool, especially also, right, that we have these like 2 exponential functions interacting with each other in our solution that came from just kind of 1 exponential function over here. That's a cool looking solution. I think this is pretty powerful, like to use the Laplace transform and come up with this as our function. And if you think about the math that we did, sure, we used some formulas for and some properties of the Laplace transform, but most of the math that we did, like there's no real calculus here outside of the hidden calculus of the Laplace transform. It's just a lot of algebra, and we get something pretty complicated. And we just did that ourselves, no problem. Oh, it's kind of a fun function to make, right? And this is going to be really useful for modeling, again, a lot of more complicated differential equations that have discontinuous forcing functions. And that's what the exciting thing about the Laplace transform is, and why we're spending this last chapter of our Intro to Differential Equations class introducing the Laplace transform. What can we do with it? How can we use it to deal with discontinuous forcing functions? In the next section, we're going to finally go back to second order differential equations. And of course, once you go to second order differential equations, you can go to any order you want, right? Just like when you did multivariable calculus, as soon as you introduce a second derivative, you see, oh, like the third derivative is just more of the same. Or if you have a second variable, which is really what I meant when I said multivariable calculus, if you have a second independent variable, you see how easy it is to add the third. It just makes things harder to visualize, but it's more of the same. So that's pretty cool. And that's where we're going. We have 2 sections left after this, one of which will be that one where we go back to second order differential equations. Should be a good time. Let me know if you have any questions, and I hope you all have a good rest of your day. Bye-bye.